Hi, and welcome to our 2:30 press conference, Holidays in Lights, Tracking Culture from Space. And our speakers are Miguel Roman, NASA Goddard Space Flight Center in Greenbelt, Maryland, and Eleanor Stokes from Yale University in New Haven, Connecticut.
All right, thanks for the opportunity. Today, we're going to show you some very pretty pictures of the Earth at night. If you are looking at this slide, what you're looking is an image of Las Vegas. I should have done a trivia about that one. Image of Las Vegas from the International Space Station on a digital SLR camera, an f2.8 focus lens for those who are following it. And you see some extremely beautiful imagery in terms of what the capabilities that we can detect from space. You see different types of lighting, and the question that that we're going to pursue on this is the dynamics of lighting and how we can use that information to address some important science questions. If you were here, if you were lucky to be here 2 years ago in this same room, you would have been participating in the first overview of the Black Marble 2012 product that was generated by colleagues from NOAA. And this is amazing imagery that has pretty much made it to every corner and every TV room in the world. And what it shows you is it's a composite of several months worth of data for 2012. And to give you some perspective, this is the very early mission for the SUMI MPP NASA's NOAA satellite. And it was an image that from an optimal set of measurements taken on the moon-free nights, you can generate this nighttime lights, and you can detect the cities. And so what a lot of the work that we do at NASA is to pursue quantitative applications for this kind of measurements, measurements that we take from Earth-time satellites. One example of that is our suite of measurements to look at the biosphere. So this is an image of CWIS, which looks at the dynamic biosphere. So you can see how the Earth is breathing. You can see the biosphere, the land, the terrestrial land, the oceans, how the cryosphere is evolving. And back in 2012, when I saw this very inspiring map, I figured, what would it take to dynamically monitor the Earth at night? And so that's the topic of this talk. If you understand the natural cycles, it's very interesting because we know that there are some peak periods in which vegetation increases and greens up in early spring and in the northern hemisphere, for example. And what we did was we wanted to detect those kind of same dynamic patterns related to human activity. And the way we did that was to examine the holidays, because during the holidays there's a ton of human activity. And so what I'm going to show to you is I'm going to go quickly through some of the results, and then I'll go in little detail of what interpret some of those results. But before that, okay, so let's go ahead and do that. But in order to go that, I just want to make it clear, this was a huge effort. It took 3 years worth of data, and it takes a lot of effort from the moment that you turn on that instrument and open up the doors of the viewers in January 19 to making sure that you have scientifically valid and useful information. A part of that means that as you are generating these records, someone has to go back and to the early mission period and make the corrections necessary to be able to use this data for scientifically useful applications, for long-term monitoring. In operational applications, you don't look back, you look forward, you're predicting weather. But at NASA, we have a capability to go back and reprocess the data, apply the best calibration, the best coefficients. And so what you're seeing here is the steps that we took to get to this point, to get to the actual lights. And I'm not going to talk about this too in detail, but we're going to really go into having fun and actually looking and interpreting the data. But just to give you some perspective, we're using an improved algorithm to generate cloud-free, to account for atmospheric effects, terrain correction effects, Terrain is a big one. If you're over land, you don't want you're mapping a city. That city can't be wobbling around. You have to have a very standard map, as well as Straylight contamination due to instrument artifacts. We're also very fortunate to have used a lunar irradiance model generated by Steve Miller, who's present here, who allowed us to use this data in quantitative applications. So a lot of the data used for nighttime, it's either before or after images, but the idea to have a reflectance-based analysis requires a really good understanding of the lunar environment at night, so that that information can either be subtracted or used for different kinds of analysis. But now, this is the message. You turn on the satellite, and it's not nighttime lights all of a sudden. There's a ton of people working outside in the trenches and making sure that that data is useful for the community. So now let's look at what we did. We examined daily holiday changes in lighting at the 3 fundamental scales of urbanization. For many years, the Heritage TMSP OLS sensor has been constrained due to performance to only country scale analysis. But for the first time, VIIRS is allowing us to do a comparison across cities and even a comparison of neighborhoods within cities. And Eleanor and I will show you some examples of how we can do that. Now, it's the holidays. We're in the US. It's Christmas. So let's first check here. So let's go to the heartland in Texas, and let me show you some imagery. This is Texas and Louisiana, some parts here, and you can see this. This is the color bar with greens and yellows and reds. And let me explain these. What you're seeing here is a difference map. It is a map that collects daily measurements for the entire holiday period in the United States. That includes the Thanksgiving all through the first week of January. You generate an estimate of the amount of lighting for that period, and then you compare it against the rest of the year. Meaning that if you see a lot of green, that means there's an increase in light output. If you see yellow, that means it remains flat, it remains constant. And if you see red, and you notice that there's not a lot of red, it should be a decrease. And green means around a 30 to 50% increase in lighting. So in other words, what you're seeing here in Dallas, in the northern parts of Dallas, in this sector here in Houston, is Christmas lights from space. Now, why are we seeing this from the VIIRS? And we all thought the nighttime lights were stable. Here's why we can see this. What's happening during the holidays is that our patterns are changing. We're becoming this weird species that we're eating more turkey and we're doing these crazy things. We're going out to Macy's and buying stuff. We are changing our patterns of behavior. But what's really interesting about the United States is that pattern in the behavior is affecting the location of demand for energy services. Now, what does that mean? It means that, let's look at some of this data again. If you look at the city of Atlanta, I put in a zoomed image here. Now look, where are the green areas? They're in the suburbs and the exurbs. In the periphery, it's creating this donut hole where you have this lighting output increase in predominantly residential regions. That's what we mean by a shift in location of activity. People are leaving work for the holiday, and they're turning on the lights. People are demanding more energy services. And we see that embedded in this data. Let me go ahead and look at other examples. Here's the DC, Baltimore, DC metro area, and an area we know well, we're from here. This is the Loudoun County in the Fairfax region, which is characterized by a lot of new housing developments based on large-scale single-family homes and with large yards that provision more space for lighting and illumination during the holiday. These are the McMansions, basically. The urban centers, however, are seeing a constant or slight decrease in energy demand services. largely because, and we believe that the reason why it's because it's a denser area where there's less space to provision lighting and the organization of those lights. We have all these images that are going to be produced, displayed on our website, and including the original geotips files for you to see, so I'm just going to go through some of them again. Here's the LA and Phoenix region. You see that the signal is very consistent across the United States. LA, it's pretty large area, and you see a lot of heterogeneous patterns in terms of the lighting increases. Phoenix is, on the other hand, a very residential area, even within the urban corridor. And so you can see greenness patterns happening even within the downtown centers. Now, this is where we are. And here's one of the things that we can do with this new refined algorithm. You have a data set that is consistent for the entire day, and that means that not only you can do this kind of dynamic compositing, but you can measure the EKG of a city. This is the average signal for a 36-month period for the entire Bay Area. And you can see here the vertical lines are showing the two New Year periods of 2013 and 2014. And you can see that we know we're seeing Christmas lights because it's a repetitive pattern. And we have developed algorithms to detect cyclical patterns in human activity from year to year. And I owe you the 2014 year. We're getting there. But as soon as we get the full reprocessing, we can get you the third year. The colors here are just some technical identification of the quality and rigor of the data set. We have multiple algorithms that identify the rigorousness and the uncertainty in the values. And so anything that's green meant that the Bay Area was completely cloud clear using majority high quality retrievals. Anything in yellow and in red meant that we had some challenges in trying to get an exact retrieval for that date. And so we're employing different algorithms based on climatologies of nighttime lights to fill those holes. The other part that you can see here is we have the monthly composited version. And you can see that in some cases, they just can't detect the very short scale patterns in human activity happening during the holidays. Even though you have a seasonal holiday, it's a hit or miss. But overall, it's detecting the overall trend very well. So it's good a product. So here's the thing. This is Bay Area. Now, the question then is, what's the national signal for the United States? So if you did this and you measure the cyclical trend for a representative sample of cities that passed our quality screening test, we have two scores, an E and an epsilon value, that determine the population of green values, the best quality values, and we use that to establish the rigorousness of the retrieval and the distribution temporally. And if you do that, you end up with 70 cities in the United States, most of them south of St. Louis. Unfortunately, we can't cope with snow. And the good thing about having reflectance is that you can quantify things, but it's too good because now you're seeing the snow BRD, the snow reflectance, which is contaminating the signal. So unfortunately, we owe you the New York City holiday signal because, unfortunately, if you live in Rochester, that we can't see it. There's just too much contamination from snow. So if you do this for the 70 cities south of St. Louis and you pick up the best, highest quality with the best cloud screening and algorithms, this is what you get. And what we're seeing essentially in this blue line is our national signal for the holiday. And this is what's really cool about this. It's showing that all cities are going through this phase of increase in holiday activity. Cities, regardless of their economic background, the majority in ethnicity, everybody in the United States is celebrating the holiday. And this is telling us something that we all as Americans know, which is that Christmas is not just a religious holiday, it is also a civic holiday. And this space-based retrieval is tracking this national shared tradition. It's amazing. Now, this is great. This is for the US. It's a Western holiday, but if you want to apply a control, you need to find someplace else. You need to objectively look at the data over cities. And then we had a debate on which country to pick. And I'm the PI, and I'm Puerto Rican, so we have to look at Puerto Rico. This is from ISS. And now here's my justification for looking at Puerto Rico. Beautiful place to go out for the holiday. If you go there, and I'm supposed to advertise, the tourism industry since I was little tells me you have to advertise Puerto Rico. So four words you need to learn if you go to Puerto Rico. Pasteles, arroz con gandules, and lechon, and you'll be fine during Christmas. You take out that bread, and it's the best gluten-free diet in the world. Now, what you're seeing here is 3 different towns in Puerto Rico, and we sampled the 30 most populous towns in Puerto Rico. And why Puerto Rico? Well, think about it. 75-degree Fahrenheit average at nighttime means more partying at night. It also means a lot more festivities, and people just don't want Christmas to finish, so they keep their lights at night through January 20th. I'm not kidding. The Puerto Rican Christmas season ends in January 20th with the San Sebastian festivity in San Juan. So excellent, excellent case study. Now, here's what's happening when you applied your routine algorithms to cluster different cities in Puerto Rico. And you can barely count, name the small towns around here because they're just clustered. But this is routinely what we have done before with nighttime lights, which is more lights equals, it's linearly proportional to more people. The more lights you have, the more people you get. But what this is missing is the holiday dynamics. And so if you add that variable into the equation, this is what you get. You get a complete clustering of cities, not just as a function of their size, not just as a function of the population density, but you're now able to classify the cultural centers, to locate the large suburbs and exurban areas, the industrial centers, and the countryside towns, meaning that you can classify cities around the world as a function of the energy behaviors of its inhabitants. Behaviors that are based on the norms, on the identities of a culture. And this is way cooler than seeing Christmas lights from space. Now, okay, so we're just seeing Christmas. Then now the other control should be, well, if this is true, if this technique is quantifiably sound, then we have to apply it across different cultures and see whether different patterns arise. And the way we did that was to examine a different holiday in a different part of the world. And Eleanor here will be talking about that different holiday.
Okay, hi, I'm Eleanor Stokes. I'm a PhD candidate at Yale University's School of Forestry and Environmental Studies. I'm in the Urbanization and Global Change group. And when I first started working with Miguel a couple of years ago, we weren't looking at the United States. The algorithm wasn't quite developed, and so we wanted to choose a place that had less aberrations in terms of humidity and clouds, so we chose the Middle East. And of course, the Middle East had a quite different energy signature than the cities in the United States. And it peaked particularly during the holy month of Ramadan. Ramadan is the 9th month of the Islamic calendar, and it lasts about 30 days in the summer. And during Ramadan, Muslims fast from dawn until dusk. And what happens is this shifts their activity to later and later in the day. So instead of seeing what Miguel was pointing out was mostly Christmas lights, we're seeing a shift in the timing of activity, not just an increase in light sources. So when people shift their activities later in the day, they're eating later, they're participating in commerce later, markets are staying open later, there's even changes in work schedules. People go to work later in many cities. There's also public activities such as the night prayer, which lasts all night long. So we're seeing increased activity in the nighttime, both because of Ramadan and also because the summers in these areas can get up to 120 degrees. So that's really quite hot, which pushes the activity further and further into the night. So it makes a great study for a satellite that takes pictures at 1 a.m. So we used this holiday to look at variations between cities in the Middle East, and we looked at countries from the most conservative, like Saudi Arabia, Iraq, Iran, to more secular or diverse countries where there's state-sanctioned freedom of religion, like Lebanon, Jordan, also Israel, which is obviously not a Muslim country at all. And what you can see on the right is the similar maps that Miguel was pointing out for Christmas, except that this time it's for Ramadan. And you can see it's a quite different pattern. So we're seeing increases in the city center, not in the exurbs. And we're also seeing some variation between the different types of countries. So in Saudi Arabia, we see a very strong Ramadan signal. That's that middle graph on the left. In Jordan, we see a pretty strong Ramadan signal. In Israel, we see no signal at all. And so these variations start to show that nighttime lights really track these cultural differences between these cities and between the countries that host them. Now, in some cities, we were surprised not to see Ramadan ubiquitously across the Middle East. In Iraq, for example, we saw very consistent negative cyclical trends. And when we started to look into this more and look at some of the Institute data about their power infrastructure there, we realized that on average in 2012, urban Iraqis only had access to power infrastructure around 13 hours a day, and that became even less in the summer when air conditioning and other loads were taxing the power infrastructure. So these dips that we're seeing in Iraqi cities are most likely the cause of vulnerable electric grids across certain countries in the Middle East. We also saw these patterns in Lebanon. And these dips improve as we move towards 2014, which is also consistent with the Institute data. Other types of activities, human activities that disrupted the normal seasonal signals we were getting from cities were geopolitical conflicts. You see very striking decreases in the nighttime light signal, for example, in Syrian cities. The top shows a 94% decrease in nighttime light levels in Aleppo, Syria, 50% in Damascus, which is the second graph. And these are very consistent with the types of findings that were found really recently using DMSP data as well. So in this way, these nighttime lights really are, in some ways, the EKG of a city. And when much of the power infrastructure or the sources are taken out by conflict, what you're left with is moonlight. And the reason you don't see that in these signals is because we've obviously removed the moonlight signal. What maybe is more surprising in terms of findings is not that cities in different countries might have different Ramadan signals, but cities within one country might also, that their power or their electricity patterns would also track cultural and social boundaries. So within Egypt, we looked at 21 districts, which we wanted to see how they related to other socioeconomic variables, such as illiteracy rates, access to sanitation, and voting preferences, which often indicate how religious or how conservative a certain district is. And we wanted to see how these changes in Ramadan, which are shown in the left graph, changes in the nighttime lights, are related to these other social and political and economic variables. And what we found is that they actually cluster really well. There's a correlation coefficient of 0.5 between changes in the Ramadan nighttime light signal and these other socioeconomic variables. And as you can see on the top, these are clusters based on socioeconomic variables, but it's showing you the nighttime light signal, and you can see how well the nighttime light signals cluster for these different groups. As you move from right to left, the clusters become lower income, and they also become more conservative. So you can see that the way that they're celebrating Ramadan is very, it's also indicative of sort of the social and political leanings of the place. The richer clusters have a much broader Ramadan signal. The poorer clusters increase towards the end, and they all actually peak at the end at the Eid, which is the biggest festival that marks the end of Ramadan. So what does this all mean? What is the takeaway? We know that in order to achieve successful climate mitigation, we're not only going to have to innovate in technology, but we're also going to have to innovate in the way we understand energy demand and the behaviors that shape that energy demand. And what we found here is that energy service demand is the aggregate of human activity, and human activity is driven not just by individual factors like price, like energy and electricity prices, but also activity is driven by social and cultural context, by what people want to participate in. And so when you look at the energy signatures, you can see those imprints, those cultural and social imprints in the energy signatures themselves.
Thanks, Eleanor. And then here's the last slide in terms of what's the implication? Why should we care? If there's so much data out there in terms of looking at social and the patterns that drive energy, of course, a lot of these are individual factors like the price of energy. But it's now that we have this new tool, and it's an objective tool, you don't have to interview someone. You can see it, and it's consistent across the world. It draws this idea that we can finally start tackling these very difficult questions about how human energy-centered research interconnects and is coupled with climate change research. I mean, if you think of it, more than 70% of the emissions in cities come from this, emissions globally comes from the cities. And if we are to follow the IPCC guidelines, which is, we have to reduce the consumption as well as develop mitigation strategies that are locally relevant. It's great that Michael Bloomberg is spending like $20 million on greening up New York City, but that plan is not going to work for Amarillo, Texas. You have to have locally relevant climate action plans that are looking at the activity patterns of different inhabitants and to look at the values and the statuses and the aspirations of a culture within the city. And we think that this is finally, this is just scratching the surface. This is what we could come up with in terms of what we understand that we're seeing. And that's a big distinction from what has been done in the past, which is just try to correlate the nighttime lights to any given factor. This is what we're seeing. We're seeing outdoor lights. We're seeing people turn on the lights as a function of some decisions that are driven both by individual patterns and by socioeconomic patterns. And hopefully there's a lot of users out there that can not just use our data, but can build new algorithms and to make it more suitable for different analysis and different investigations. And that's it. We'll take questions.
Okay, are there any questions?
Oh, and thanks to the NASA Goddard interns, there was like 40 terabytes of data that we have to reduce for this. Yeah, it's a NASA does a lot of data-driven projects, and we couldn't do it without our interns. All right?
Okay, thank you. Are there any questions in the room?
Hi, Ken Chang, New York Times. So I imagine San Francisco has a greater percentage of energy-efficient LED bulbs versus other places. I was wondering, can you pick that out in the frequency?
Oh boy. The quick answer is that we cannot. And the main reason is, it gets a little technical, but what happens is that we have a nighttime channel that begins right around the red edge, and it goes into the EIR. If you look at the Nobel Prize of Physics, you know that LED lights are made with blue, with green, and with red LEDs. Combined together, you get white. So if you the inability to get the 470, the anything under 490, it's very difficult. What we, however, can see is, as cities move into this greening phase of illumination, the lights will start becoming dim. So you may attribute that to this green up in LEDs, but it's ideally we should have two channels, one in the LED section and then one in the other sections. And this is really not that technically difficult to do. It's very low-hanging fruit. It's just a matter of changing lenses on future sensors. And we are very excited to know that. We're currently, this has set out some discussion as to how do we do that. And there's real consensus within our satellite community to make those changes possible.
Fernando Burrell, ESA, European Space Agency. I have a question regarding if there is a discussion at NASA concerning privacy issues regarding this data, because you're essentially monitoring mass movement which allows not only calculations concerning climate change, right, but also concerning economic impact, for example, where to put up billboards, how do we monitor people moving around at nighttime. Well, this are also parts of your considerations in this research.
Well, we have a data policy. NASA Earth Science datasets are freely available to the community, same as ESA's. And sometimes we stumble upon these new applications, but the role of what we do in Earth Science is to enable the science. We don't house a lot of economists at Goddard. We wish we could, but what we do is we take this raw data and we turn it into scientifically useful information. And then it's up to the policymakers to decide what to do with it. Having said that, all these things in terms of economic viability, national security, these things are societal benefit areas. And we are gonna, we're gonna use the satellites as much as we can for applications to benefit our citizens because they're paying for it.
Harvey Lyford, freelance, and pardon the voice. I'd like to go back to the earliest slides where you showed Texas, for example, in the green. That period of about 1 month showing the difference is compared to what? A full year, including that period, or the 9 months or 11 months excluding that period?
The latter. It computes that for the rest of the year, not including Christmas.
Okay.
Otherwise, you have this bias inherent on it. And yeah, so that's, yeah.
Yeah, and I was actually going to say, that's not just a single year. What we've done is taken several years and we've parsed out the seasonal signal, which is the signal that repeats every year. And so you're not looking at just like 2011 there, you're looking at sort of a conglomerate from all 3 years.
Rick Lovett, freelance. I've got a somewhat similar question, I think, and I may have missed this right at the start. Obviously, you have different lengths of nighttime, how, and actually that could change people's behavior significantly over a 6-month cycle. But I heard you say at one point you're taking the measurements at 1 a.m., or so that's what you're doing all around the year on this?
Yeah.
About approximately, depends on latitude, but this is a polar orbiting satellite, so it crosses the equator every day at 1:30 a.m. in the morning and at 1:30 p.m. And because it's a wide swath, however, you're getting more looks as it goes through a swath at high latitude, so you get into all the way from 10 p.m. to about 3 a.m. in the morning, right, Robert? Something around that time. We have our expert orbital and geolocation guy here. So, but yeah, so that's so very late at night. Yeah,
Yeah,
and just wanted to point out that the DMSP is actually more optimal in that sense because it captures the early 10:30 p.m. It's still very late. So the ideal, if you give me $30 million and I put a camera on the ISS, would be to certainly track multiple times at night and multiple channels to detect different types of light, because that would be exciting, because that way you can detect different economic sectors, because the Walmarts are using fluorescence and you have residential areas going now greener, so that will be very exciting.
But you're basically capturing people who leave their lights on late then.
Yeah, and the hotels leaving the Christmas lights all day long and all these. Yeah.
But that's not true in the Middle East. I think the Middle East actually has quite a bit of activity at 1 a.m. So it depends on where you are.
Yeah.
Any other questions in the room? Any questions on the chat? Okay, any other questions? No? Okay, thank you. That concludes our last and final press conference of today. We will see you back here at, I think it's 8 a.m. tomorrow for the Rosetta press conference. Thanks.